The ships that carried the world's cargo in the 1700s were not built in factories. There were no power saws, no cranes, no metal fastening machines, no dry docks that could be flooded and drained at will. A first-rate warship of the line in that era weighed somewhere between 2,000 and 3,000 tons when fully loaded. Its keel alone could run 150 feet. The main mast rose over 200 feet from deck to truck. Every single piece of that vessel was cut, shaped, hauled, fitted, and fastened by hand, in open yards built on riverbanks or harbor edges, by men working with broadaxes, adzes, hand augers, and the accumulated knowledge of a trade that passed from father to son across generations. Before steam-powered sawmills, before iron frames, before electric hoists, this is how they did it. The problem was not just size, it was material. A ship of the line required somewhere around 2,000 mature oak trees, each selected for a specific grain, curve, or density. Finding that timber was itself a years-long operation before the first plank hit the ground. The English oak used by the Royal Navy had to be at least 80 years old to reach the density needed for frames that could absorb cannon shot without splitting. Thinner planking near the waterline demanded a tighter grain, one that resisted boring marine worms that could riddle an unprotected hull in tropical waters within a season. Timber for deck beams needed a different character again, straight-grained and stiff enough to carry the weight of cannon, crew, and shot without deflecting. One ship required dozens of distinct timber types, and none of them could simply be ordered from a single supplier. Curved timber for the knee pieces, the natural bends where hull planks met the structural ribs, could not be sawn into shape. It had to be found already curved, grown that way in the forest over decades, in a form called compass timber. Sourcing agents walked English woodlands for years before a keel was laid, cataloguing trees by shape and grain for eventual harvest. The tree selected for a specific knee had often been marked a decade before the ship it was destined for had even been ordered. England's oak forests were shrinking fast under this demand by the mid-1700s, and the Navy found itself sourcing compass timber from New England, from Scandinavia, from the Baltic ports, adding months to the supply chain before construction even began. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. The shipwright's yard sat on flat ground close to water. A vessel of any real size could not be moved far once the keel was laid, so the yard was positioned so that the completed hull could be launched directly into the river or harbor at the end of construction. The keel went down first, a single continuous backbone of elm, chosen for its resistance to rot when submerged, typically bolted in sections because no single tree grew long enough. On that keel, the shipwrights raised the stem at the bow and the stern post at the stern, both cut from massive curved oak, and joined them to the keel with iron bolts driven through pre-bored holes and clenched over iron rings on the opposing face. The keel assembly had to be perfectly level along its entire length, and the yardmen checked it with plumb lines and long, straight battens before a single frame was raised. An error at this stage propagated through every part of the build that followed. The frames came next. Each frame was the rib of the ship, a curved timber assembly rising from the keel on both sides and meeting at the top to form the cross-section of the hull at that point. A large ship had well over 100 frames spaced roughly a foot apart along the keel. Each frame was itself built from multiple pieces of timber scarfed together, because no single piece of wood grew in the right curve for the full height of a hull side. Scarf joints were cut with a saw and dressed with a chisel until the mating surfaces were perfectly flat and interlocked over a long diagonal cut, distributing the load across the greatest possible area of wood. The pieces were then joined with iron bolts and wooden tree nails before the whole assembled frame was raised into position on the keel. Small frames went up with muscle and rope. The larger ones required a system of tackles rigged from temporary posts set in the ground around the building slip, with gangs of men hauling on the falls while others guided the frame upright with handspikes. The shaping of individual frame pieces was done with a broadaxe and an adze. The broadaxe was swung to remove bulk material, taking chips the size of a man's palm with each stroke, reducing a raw log toward its final dimension in minutes. The adze came after, a tool with a curved blade set at right angles to the handle, swung between the legs in a controlled arc that gave the wielder precise command over the depth of each cut. A skilled adzman could clean a timber surface nearly as smooth as a plane would leave it, working entirely by eye and feel, reading the grain of the wood as he went, and adjusting his stroke angle to stay ahead of any tendency to split. These were not unskilled men swinging tools at random. They were tradesmen who had spent years learning to work wood at full scale in 3 dimensions, producing curved surfaces that had to mate accurately with adjoining pieces they had not yet seen. The frames were raised one by one and held temporarily in position by ribbons, long, flexible battens of pine nailed across the outside of the frames to hold them plumb and in line while the permanent fastening went on. Alignment was everything. A frame set out of square by even a fraction of a degree would throw the planking off at that point, creating a hollow that would hold water and begin to rot from inside the hull before the ship ever reached open water. Checking alignment was done with plumb lines, with long, straight battens, and with the eye of a master shipwright walking the length of the hull and sighting down each row of frames the way a carpenter sights a door edge. The master shipwright carried the shape of the entire hull in his head. The drawings that existed were guides. The judgment of whether a specific piece was right was his alone. Planking followed framing. The hull planks, called strakes, ran the full length of the hull and required bending to conform to the hull's curve, which changed from near flat at the keel to a sharp turn at the bilge and back out again toward the waterline. Forcing a 2-inch thick plank of seasoned oak around that curve without steam was impossible. A steam box, a long enclosed wooden chamber connected to a boiler, received the plank and held it under steam pressure for roughly an hour per inch of thickness. When the plank came out, it was flexible enough to be bent around the hull curve and clamped in position with iron dogs, heavy staple-shaped fasteners, driven into the frame face to hold the plank while it cooled and took its set. Shipwrights worked fast. The plank began to stiffen the moment it left the steam box, and a plank that cooled before it was fully home had to go back in for another hour. Time was money, in a yard on contract, and every failed bending added to the cost and the pressure. Once in position, each plank was fastened with wooden tree nails, round pegs of locust or Osage orange driven through pre-bored holes and wedged at both ends so they expanded into the hole and locked tight. Iron bolts went through the thicker structural members at the frames. Caulking came last on each strake. Oakum, the fibers of old rope teased apart by hand into loose bundles, was driven into the seam between planks with a caulking iron and mallet, compressing the fibers into the gap until the seam was solid. Hot pitch followed, ladled over the oakum to seal it against water. The smell of pine pitch and steam and fresh-cut oak hung over a working yard constantly. Anyone who walked in from the street knew what was being built before they saw a single timber. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. The masts presented a separate problem entirely. No single tree grew tall enough or straight enough for a main mast on a large ship, so the masts were built up from multiple pieces of timber called made masts, and this was a specialized trade within the trade. The pieces were arranged around a central core timber, fitted into one another along carefully shaped scarfs, and bound together with iron hoops driven on hot and allowed to cool and contract around the assembled mast. The hoop fitting was done by a blacksmith working alongside the mast makers, the hoops heated in a portable forge until they expanded enough to slip over the mast section, then quenched with water to shrink them tight. A first-rate ship's main mast, built this way from separate timber sections, had to carry over 3,000 square feet of canvas in its lower sail alone, with the full force of an Atlantic gale trying to pull the whole assembly sideways out of the keel. The integrity of the made mast was not theoretical, it was tested on every ocean crossing, and the consequences of failure at sea, with no dry dock within 1,000 miles, were immediate and catastrophic. Rigging a completed ship required another set of hands with another body of knowledge. The standing rigging, the permanent ropes and cables that supported the masts, was made of tarred hemp and ran in a precise system of shrouds, stays, and backstays that had been developed and refined over centuries. Getting the tension wrong meant a mast that would fail under pressure at sea. The riggers worked from staging hung from the masts themselves, splicing and seizing the wire-thick ropes with marlin spikes and bare hands in weather that did not pause for their convenience. An experienced rigger could judge the tension of a stay by feel, pressing it with his thumb the way a doctor checks a pulse, reading the resistance as either too slack or too hard, and adjusting accordingly. That knowledge did not come from a manual. It came from years on the water and in the yard. The running rigging, the movable ropes that controlled the sails, added another layer of complexity entirely. A large ship of the line carried over 20 miles of rope in its total rigging, each line with a specific name, a specific function, and a specific consequence if it was rigged wrong or handled late in a squall. Teaching a new hand the rigging of a first-rate ship took months. Knowing it well enough to work it in the dark, in bad weather, by feel and memory alone, took years. The labor involved in a major yard defied easy counting. The Royal Navy's largest yards at Deptford, Woolwich, and Portsmouth employed between 1,000 and 3,000 men at peak periods of wartime construction. The trades present in a single yard included shipwrights, caulkers, sawyers, joiners, smiths, riggers, rope makers, painters, and laborers of no specific trade who carried timber, turned capstans, and moved materials by hand. The sawyers worked in pits beneath saw frames, one man above and one man below, pulling a long, two-handed saw through a log laid across the pit edge. The man in the pit caught the sawdust in his face on every downstroke. He worked in dim light below ground level, in a space too narrow to straighten up, for the length of a full working day. No record of his name went into the ship's logbook. The danger in a working yard was constant, and largely unremarked in official records. Heavy timber moved on rollers across uneven ground, pinning feet and crushing hands when control was lost. Hoisting tackles broke without warning. Adzes slipped on wet wood. Men working overhead dropped tools onto workers below with no time to call out. The pitch heated in open cauldrons for caulking burned skin through clothing when it spilled. Burns, crushed hands, and falls from half-finished frames were ordinary enough to require no special documentation. What the records do capture, though imperfectly, is the slower toll on the sawyers and caulkers. The hardwood dust the sawyers breathed in the pit over years caused the same gradual destruction of lung tissue that stone dust did to quarrymen. The oakum-pickers who teased old rope apart by hand, hour after hour, shredded their fingertips to the point where some could no longer hold a tool by the end of a working season. The work produced extraordinary ships. What it cost the men who built them was not entered in the ledger beside the timber costs and the iron bolt weights. Construction of a single first-rate ship took between 3 and 5 years under ordinary conditions. Speed was possible during wartime, and the consequences of that speed were predictable. Ships built in haste used unseasoned timber because there was no time to wait for the wood to dry. Unseasoned oak shrank as it dried after launching, opening the seams and putting enormous stress on the fastenings throughout the hull. Surveys of ships built quickly during wartime routinely found structural decay beginning within 4 years of launch, where a well-seasoned hull might last 25. The shipwrights who built those vessels knew this when they built them. The admirals who ordered them built on deadline knew it too. Speed, as with the American railroad, was the financial and strategic model. Permanence was someone else's problem. The iron-hulled steamer did not replace the wooden warship in a single stroke. The transition ran roughly from 1820 to 1880, with hybrid ships appearing in the middle decades, iron frames planked in wood, combining the structural advantages of metal with the tools and workforce of an industry that did not yet know how to work steel at scale. The last all-timber first-rate warships were ordered in the 1840s. By that point, the steam sawmill had already changed the economics of timber preparation, reducing to minutes work that had taken a full day's pit sawing. Power tools arrived after that in sequence: the band saw, the steam-driven boring machine, the hydraulic frame-bending press. Each one reduced the number of skilled hands required to move a hull from keel to launch, and each one made the old knowledge slightly harder to justify paying for. Some physical evidence of this work survives. The Mary Rose, a 16th-century English warship raised from the Solent in 1982, shows the frame construction and treenail fastening of the period in preserved detail. The USS Constitution, launched in 1797 and still afloat in Boston Harbor, has been rebuilt using traditional methods more than once. The craftsmen who worked on her last major restoration in the 1990s found that several of the original joinery techniques had to be relearned from the ship itself, because no living shipwright still practiced them at full scale. The knowledge had been carried in the wood long after it stopped being carried by people. What those men built in open yards along the Thames, the Loire, and the Merrimack, with broadaxes and adzes and steam boxes, and the inherited understanding of how a tree grows and how a hull moves through water, lasted long enough to move armies, empires, and cargo across every ocean on Earth. The tools that replaced them were faster. Not one of them produced a better hull. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.